All right, so yesterday we derived one equation. I mean, yeah, we kind of show the equation, and I think we stop right at this equation over here, no? Okay, and we said that there were two general cases. That was reverse bending plus static torque, and reverse bending with reverse shear, no? The two cases. So now it's going to be very simple. Let's see how the equation the general equation will simplify for each one of these cases, and then we do an example. Let me know if I need to move the page because I cannot see it from here, okay? All right, so for the first case, so let's say case one is generally the one that is used the most, which basically considers reverse bending plus static torque. So here I just want to do here a clarification is that in this notation, really compared to the Goodman line, reverse is basically the same thing as fluctuating, okay? All right, so you don't think that really completely two different methods. Okay, so if we have reverse bending, we're going to say that the average, which I think is the one we call the membrane on the other formulation, is equal to 0. So basically, what does that mean? In this case, we just assume that everything is rotating about this value here. There is no medium or mid-range value. And here we're going to assume that the fluctuating shear or alternate fluctuating equal to alternating. Everything is notation, it's not important. And this one will also be equal to 0. So substituting into, I don't have the notes from the other day, but I don't know if we gave a name to that equation. Substitute into that equation, just give it a name. The one we just finished last lecture. Okay, so just call it whatever. And do we use a letter A, B, or let's just call it A in our case. So substituting into A. It simplifies to sigma sub R, which is the reverse. Well, actually, oh, okay, I changed the order here. K sub T as yield as endurance. Everything squared plus 3 times the average shear squared needs to be lower or equal to the S yield divided by the N. I think we use lowercase n if I remember properly, square. Okay, I'm going to leave it as it is here, and then we're going to do case 2, which is the most general but not as widely used, which is reverse bending plus reverse torque. So in that case, again, we're going to have, we assume this one will be equal to 0. Now we assume the average shear stress will be equal to 0. And I can write here substituting into A, it simplifies to Y as endurance. So the first term doesn't change. The only thing that changes is the second term. Plus 3 times d tau sub r k sub t as y over s endurance. Everything squared must be lower or equal to s yield. No, sigma r is the alternating or the reverse. Remember here, reverse fluctuating. Like we are over here. So basically, the only thing I did is go and substitute for whatever simplification you do into this equation here. All right. But this is important one, and to know what happened. So, maybe let's discuss here this equation. Okay, since we are here and we have time. So here, this value that they put average. What does that mean? What are those values over here average? Can I do a figure here? Those will be the values, for example, if we take here in function of time, the stress or the shear, right? If initially there is no load, this will be between a 0 value. Is that correct? But let's say that initially you have a load. So in that case, what will happen? The fluctuating, the reverse or the alternating is going to be about a fixed value. Does that make sense? Yes? Okay, that's what these values are over here on the average, is that initially there's an average force. So for example, if you have a torque, if you have a shaft, let's say initially there is a constant force on it. So there, this will create a constant bending stress, normal stress, and also create a normal, an average normal stress, and this will also create an average bending stress, no? That will be constant. And then the structure will be fluctuating between these values. Okay, and now these are the values due to the dynamic load. You see, these ones are related to the reverse or alternating or fluctuating, whatever you want. So these values here are related to the static loading. These two values over here are related to the dynamic loading. Okay, that's what's important here to understand. All right, so let's do one example. So let me write it over here since we have time. So let's say A revolving shaft carries a bending moment of 20,000 inch per pound. So when you read a problem, so if this, you read this. So what does that mean? That means that it's going to carry an average value for the bending stress, no? That will be constant. Yeah, this will be related to the static loading. And a torque of 80,000 inch per pound. Okay, so look at it. Okay, so let's see now what they say. Assume that the torque, okay, so now they come into fluctuating loads. So the torque fluctuates 20% each way from the mean value. Okay. So let's put it here. If the stress concentration factor for bending and torsion is 1.35. Determine if the design is safe for an endurance stress of 44,000, a yield stress of 90,000, or this one should be PSI. Forgot for the other one. And a diameter of 3.375 inch. Okay, so here I'm going to need your help with the calculation. So let's see. Always when you read a program statement, first thing to do is some type of three-point diagram. Let's say we are here, all right. Okay, so let's see. A revolving shaft carries a bending moment of 20. So let's say here I will put N equals 27,000 inch per pound. Now they tell you that the diameter is 3.375. And that is a torque. Let me put this way, the torque equal to 80,000 inch LB. That fluctuates.
You're going on to the left, because you're turning on to the left, right?
This one I'm going to counterclockwise. Oh, why do I need to turn to the left?
Saying is it going to the left?
It doesn't matter if you go clockwise or counterclockwise. I just made it counterclockwise because that's the way I do it generally.
Right.
Just to show that it's rotating. Okay, so now what I will do, personally, since I need to find it, let's see what is our initial equation. The one we had initially, okay? And I will start from zero. So let's go here, recalling. The equation that we have, sigma average plus K of T sigma sub R Sy over S endurance squared plus 3 times tau average plus K sub T sigma sub R S yield S endurance, everything squared, and it should be equal to Sy over N squared. Wait, did I? You see, there's also a safety factor. Okay, let's add a safety factor here for SE, and let's say an N here. I'm just gonna add over here N safety factor, so we made it more complete this way. Equal to.
We're not solving for the safety factor. The improvement is safe.
No, basically what we're going to compare here is to know if this value here on the right hand side of the equation is basically bigger or lower than this one.
Right.
Does that make sense? I mean, it could be a question to find for the safety factor, but this is not the case. So again, here to me it will be important, okay? Because this is the part that doesn't mean it's only just one answer, will depend on your design, no, as an engineer. So in this case, what are we considering? And you have to do the calculation for me because I don't have the calculations. So in this case, let's first look at the bending. With the bending load, we will be looking at the static plus dynamic, only the static or only the dynamic? You read this problem. What do you think we'll be doing? The bending moment, we create what? We create like the static loading, dynamic loading, or the bending moments. So you want, okay, that would be assumption to dynamic. Would that be okay? Okay, so you want to create dynamic. So let's over here. All right. So let's over here. Let's first look here. Bending moment. M equal to 27,000 inch LB. Okay, I'm doing this using your assumptions. So if that is the case that you are doing, if you say this is just producing a dynamic, then you are assuming that the value will be zero, no? That's what you just told me. You're just going to create this one. This is the static term. This is the dynamic term. So then let's see what will be then. So then what does that mean? That we'll be solving here for sigma sub R. If you want, let's say we'll be here to, which will be equal to sigma X. So in this case, it should be equal to what? M times what? what will be the maximum stress? D over 2, okay, at the outside, and now we need to divide this by what will be IXX. That probably gonna need your help over here. What will be XX? Remember properly is pi over 64 diameter to the fourth. Let's see, this will give us what? The sigma sub r will be equal to m times d over 2 divided by pi over 64 e to the fourth. So this will give us what? M 32m divided by pi d to the cube. Can someone do that calculation, please? You see, I try to simplify for you. I do symbolic as long as I can. Guys, the best way to understand the problem is to do the problems in class, all of us together. Okay? Do the calculation. So 7,000 0.9. Then just for this case, can we just put 7,154? It will be safer, no? Anyway. Okay, you want to be accurate, you can do accurate. Okay, but let's do this. Okay. So we know K of T. What will be K of T? K of T will be here in this problem. They say also that K of T is how much? Oh, wait, stress concentration factor is 1.35. All right, a safety factor, let's use 2.5. Okay, sorry for that. Change this. Otherwise, it's going to become 2.5. Okay, so we took care of this term over here. Now let's take care of the other term. So now let's discuss the torque. So the torque is going to produce what? It's going to produce static only, dynamic only, or static and dynamic. This is your interpretation. This is what you need to do as an engineer, no? Then the rest is just to substitute into equations. I mean, dynamic is going to be for sure, it's moving.
But it's a static component, right? Because it's not fluctuating about 0, it's fluctuating about 8,000.
Perfect. Yeah. So that's exactly what I wanted to hear. So now let's look at this. Maybe we can do a figure. So basically now we're going to look at the torque. Which is T equal to 80,000. So for this one, you said exactly what I wanted to hear. Oops, okay. Time, this will be the shear. What did you just say? Is that it will be fluctuating here between the whatever stress will be due to the 80,000. So let's say it will be the what? TR over J now, the constant value. And then let's say here we have the plus 20%, minus 20%. So it will be something like this. So this will be here the tau average again from the figure. Okay, so in this case, what we're gonna have? Tau average is gonna be equal to the TR over J. And again, this will be equal to what? T, what will be the shear maximum? The outside radius divided by J. We're going to do as before. What is J? Should be pi is twice the moment of inertia. So if we do the substitution here, you will get what? 16 T divided by pi e to the cube. Which is equal to what? Guys, remember that when we do this in class, this is the time to ask me as many questions as you want. All right? Don't let yourself not understand something because it's like the snowball effect.
10,590.
Okay, that's somebody back up that one. Somebody else? Perfect. Okay. So now we did this. Now we need to find the sigma sub r in our equation, which would be the fluctuating or the reverse or whatever you want to call it. What do we know? How much is that one? It's simply 20%, no? So what can you do? We multiply the value 20%. So what would that give you? The same value as before, plus 20% will be whatever, 12, almost 13,000, I guess. 12, so 1, 2, 7, 1, 8. Okay. Yes, sir. Okay, so now what do we need to do? We need to go back and substitute into this equation. Okay, so let's just say here. So substituting into A sub T sigma sub R S sub Y S endurance square plus 3 times the average shear plus K sub T tau sub R SY as endurance. Everything square needs to be equal that S over N square. So let's see what we get. I mean, now it's just a matter to substitute values. So let's do it. So K of T we say was equal to what? 1.35. So 1.35 times sigma sub R, we say 7,154 times the yield value is given to us to be 90,000 divided by the endurance value, which is 44,000. everything squared plus 3 times the average that we calculate to be here, 10,598 plus 1.35. I run out of space, but it doesn't matter. Tau sub R 12,718 times 90,000 divided by 44,000. Square needs to be lower. Sorry for that, guys. I know I'm putting these values now very close to each other. Square. So what is SY is 90,000 divided by, what do we say for N at the end, 2.5. So, I mean, sorry for that. I know you have to be doing these calculations, but let me know what you find out here. What do you find? Let's just do the right hand side. What do you find for the right hand side? 90,000 divided by 2.5 squared. It's probably a huge number, but it doesn't matter. What do you get for that one?
The entire side, I got, 30.
For the right hand side or the left hand side? So what did you find? 6.660. Okay. Right now you need to do the easy one, which is on the right hand side.
I got 4.44 times 10 to the.
Somebody else, 4.44. Yeah. Right hand side is okay. 4.44. 10 to the 9.
The right side, I got it.
Yeah,
And I also got something related to the left side.
Wait, why? That's your two. Oh, you changed it.
Yeah.
Okay, and that number's not.
yeah, because I got 1.296.
Yeah, I got 1.296 times.
Okay, so I just put 1.3 then 10 to the 9.
Yeah, 1.3. On the left side, I got it.
Somebody check the left hand side.
The left side, I got 2.48 times 10 to the 9.
Did you change anything on the left side?
No,
I
you
got
know,
that, when I plugged that in.
you got that value.
I got that value.
Okay, so guys, check. Okay, no application, but let's go for this one. They can 2 persons got that one and 2 got this one. Okay, but again, that's what I'm saying. If it's good if you do that in class, you see that we are having the whole class is having time, I mean, not difficult time, but we need to do this multiple times to get to the right value. If you don't practice, what's going to happen in class, the day of the exam, you're not going to get it, no? I know that you know how to use a calculator. That's what I'm saying. You know how to use it. The reason is you don't practice, so you might find something wrong in your calculation, no? That is not that you don't understand using your calculator. Okay, that's what I say, and you need to practice. So over here, then, what is your conclusion? So conclusion here, you can say design is not safe. So since we have plenty of time, I think so, no? I don't think it's, what time is it? 10:23. We have what, until 11?
Yeah.
Okay, so, and basically, this is almost the last thing that Matteo was speaking. I told you we're way in advance. I mean, I don't know if we're in advance, so. Anyway, I'm supposedly the one I developed this course like many years ago. I had shaft design in detail. Last time I met the instructor that are teaching this with me, they all said that they cut the shaft design, the whole thing. So if we want to cover all the same material, basically that's it. So from now on, like I told you the other day, the only thing we do is going back, taking problems and solving them together in class. No? Okay. But if we have time, okay, let's get on something new here. So design is not safe. So let's ask over here. What should be the shaft diameter for a safe design? So obviously, in this case, what I will do is what is the best option? I will go and do it with MATLAB. I mean, MATLAB or software, because I mean, or you can put the old times they will put all these calculations into Excel, no? So you can change the values, but let's be a little bit more engineer and do that in MATLAB, no? And see what should be the value for this, for the diameter, so that is safe. So help me here a little bit. Try to do this with you here live. All right. What is this? Okay, I think this is an old example from us. Don't show me again. New script. I like script. I'm not that good at it because I find out that supposedly when you create a section, you can only execute that section. And then I get crazy because I like to execute everything. Okay. So here, let's say what I do all the time in this, I do clear all. If you got another good habits, let me know. Okay. Let's save this one file, save as. Here we go, Spring 2023. So let's see MATLAB. Okay, can we call this one shaft? Oops, sorry. Design 1. Oh, and let's put here. Here we're using the von Mises criteria. That way you will have this one. Okay, save. So, okay, since we have plenty of time, let's say ME304, all this stuff is not necessary. Shaft design for von Mises failure criteria. I'll give you this file at the end of the class, okay? Just remind me, I will put it in Canvas. So let's say here, let's say what is given. So let's see what is given. The bending moment was how much? 27,000. So if you want to be detailed, you can put over here, whatever, bending moment. Bending moment in inch LB. Then what do we have? Torque equal to 80,000. Correct me if I'm wrong, okay? Just doing that by memory. We can put here torque. Inch LB. I'll give you this file, okay? What else did we have? Safety factor of 2.5. And then we have K sub T. How much was K sub T? 1.35. Okay, 1.5. Oops. All right, stress, concentration factor. Then what do we have? We have also those SY. How much was SY? 44,000?
That's what I was.
Oh, that's it. It's 90,000. This is the endurance one. 90,000. So let's say this should be what? The yield stress. You are welcome to use sigma y, okay? As you, that one is the one that's 44, no?
Yes.
Thank you. This was the ultimate stress. And guys, I mean, I know now for classes, will be good if you do this because sometimes on the assignment you might have to reuse, you might have to reuse these ones and you can check your answers, no? Okay. I'm just doing detail because we have time. Oh, okay, yes, it's endurance stress. I don't know why. Thank you. You are paying more attention that I am here. Endurance stress. What else should we have? Let's say, and then we have here, let me just jump one value. Let's say here, initial diameter. What was our initial diameter? 3.375. Okay. Let's say here, shaft diameter. Inches here, if I wanted to be more detailed, I should have as well put PSI. PSI. Okay, leave a couple of spaces here, all right? Then we go back or do the for loop, but let's just put the stuff that we know. So let's see, sigma R, we say what's going to be equal to what? M times D over 2. So maybe we can do stuff outside as well. Okay, let me put some stuff over here. Then here we can have what? I was equal to pi over 64 times D to the 4th. Moment of inertia. What should be the units for this? Perfect. And then we have J here, which is pi divided by 32 times D to the 4th. And this one is also a moment of inertia, but generally they call it polar moment of inertia. Inertia inches to the 4th. Okay. So let's say we have this divided by I. Correct? Even if I was you, I would do probably this. So that way you can use this for any problem. SG in our case, we say that this would be equal to what? 0, no? Let's make a general problem. Then what do we have? Okay, let's start, let's write this and then we do it. This would be T times D over 2 divided by J. And now in this problem, we say that the tau sub R was equal to what? 1.2 times the tau average. Okay, so maybe let's start here since we have time. What should be this value over here? So let's say it would be average, static, normal stress. Now, if I need to write something, What would be this one? How do you want to call this one? Want to call it fluctuating, reverse, alternating, dynamic?
Reverse.
All right, reverse, perfect. I mean, I don't mind, I'm kind of just what they do. So reverse,
I see the R that makes no sense.
I know that's why they use it. So normal stress. Okay, but I'm gonna add here. What is the notation we use when we use the Goodman sign? I think it was called alternating, no? That way we can make the connection, all right? Now this one will be what? Average static shear stress. And this one we can call it reverse alternated shear stress. And now maybe help me over here. I'm going to write this as left hand side and right hand side. So left hand side is, what is it? SG average plus KT, no? KT times SG sub R, oops, about sigma, SG sub R times S Y
Over
S endurance, all that stuff square plus, and let me do this, might be a little bit faster. Maybe, yes, maybe not, I don't know. Copy paste. So this should be now the tau average plus K sub T tau sub R, and the rest should be the same, no?
Then just times 3 out front. 3.
Oh, yeah, it's 3 because it's one missing, correct. So this will be the left hand side. Maybe we can go and check now our calculations for the equal that stuff. That way we know. And right hand side is SY divided by N.
Yeah.
Everything squared. Okay, so initially let's do the first part of the problem. So let's see, where are we here? Okay, so this is the first part of the problem. Basically, this is what we just did. So let's run this one. So right hand side, yes, 1.2960 10 to the 9. We put 1.3 good enough, and 6.6605 10 to the 9. Okay? All right, so we say not safe. Now, basically, let's see what we need to do here. What can we do this? What could be the easiest way to do this? We can do a loop, no? Let's say for what can we do this? There's multiple ways, but let's say this one. Let's do 20 cases here and see what happens. We can do more. Let's say here will be this should be an equal, not a plus. Equal. So let's put over here that. Just put over here now the, let's say the initial. It might be a little bit easier with this. That way I only change one. Here I can put just D will be equal to D initial plus what do you want the increment to be? Or is there a command called increment? One, whatever, 0.2. 1. Okay. So basically what I'm saying here is that over here, or maybe I have to do the other way around. Let's do this here. I put the increment outside now. afterwards.
So,
I just go beforehand.
Yeah. Control Z.
I'll put it outside of the for loop too, if you want.
Yes. Let's put it here outside. Increment, what do we say? 0.1? 0.2, I don't remember. All right, so now at the end, what do we need to do over here? Maybe we can just do now an if condition. So let's say if left hand side lower or equal to right hand side. What does that mean? Display whatever, not save.
Less than that. Either it's equal, then it's safe.
That's fine. All right. Else display save design. And for the oops. Why did you do this stuff here? Okay. Yeah, it's probably my fault, like always. I always tell you, when you do a mistake, John, is always your fault and not the software. So and then this will be the end for the loop, no?
Display function.
You just forgot the P in the else display.
Okay, yeah. Display. And that's camera here. Okay. Why did I put this stuff? I never put this stuff. Okay. So hopefully now it will work. Let's see what will happen.
You have to.
We'll call it the
You probably need to move those like inertia, moment of inertia.
okay, let's see, but this one here, no?
Yeah, but it's not set before you click the moment of inertia. It's put the I and the J inside. The I and J lines have to go in the for loop, so.
Why is that going to change? Oh, because it changed the value.
Yeah.
Absolutely correct. You see, that's why I needed your help here. Okay, so here we come. So I mean, this is not needed, but generally I like to organize personally this way when you do a for loop. But everything on the same, at the same level.
Control AI. Do that for you.
Really? Let me undo this stuff. I want to learn something. So now I can just hit Control AI.
Control A and then Control I.
Control A. And now what?
Control I.
Yeah, but this is going to do the whole document.
Yeah, it'll indent it properly.
Just select everything you control it. Everything you want.
So you'll see it kind of adjusted it.
Okay, that's perfect. You see, I learned something. I can also learn something from you guys.
You might want to put a comment in the initial I and J outside of the for loop, or else it'll still error.
This one here?
No, like.
Oh, in here, yeah. So let me just, can I just put this. Correct. You see, you're good at this. All right, so hopefully now, okay, so save design already right away. So maybe I should have seen what should be the value. So maybe when it's save design, and I put here plot DI or D. How do we call that one? D. And see what happened, no? So let's see, save design is already at. It looks like right away.
I don't think it ever. How did you do your increment? Go up in your for loop.
Yeah, let's see what happened here. So let's do this here. What happened?
D equals DI plus increment. So I think it's gonna be.
It's always going to take the same one. Okay.
Increment times I. You do increment
Correct.
times I, which you do.
Yeah.
And again, the first one met the criteria.
And then we go. But it's still going to be the first one because it looked like some of the first one is started to the right. Oh, so not save, not save. That doesn't make sense.
Not save, not save.
That's the first one.
That doesn't make sense. That doesn't make sense.
How do we have the boundary statement wrong? Like if it's safe or not safe, maybe we flipped them.
Let's see what do we do here. If left hand side is lower than right side, it is not safe. Oh, it's reverse. See, I was going too fast. If left hand side is higher,
Right.
it's not safe, else would be this. There we go.
It'll flip everything.
Yeah, we'll flip everything. So now basically we can say that it's safe starting at. So we do increment of 1.5, safe design, safe design. Safe design. So it looks like right away now. But... And it would be good to see one that is not safe. No, here we go. So not safe for this one. So for the whatever, first one. So 3.375 is the first one, and it doesn't get safe until you get to a radius of 4.475. Okay. Yeah, almost binding. So we can just go over here to the page if you want. Just have one little line over here and say what. So let's over here using MATLAB code. It is found that the minimum diameter for safe design is D equal to what, to 4.470 was. I think that's what it was, 4.475. So it's control index basically, no? In MATLAB. Control A is to select everything. Control index there.
There's also a button on the top that you can also pick.
I mean, maybe you can then teach me something else, like because it drives me crazy. I use this. Let's just do like a little summary. Okay, so basically, I'm almost going to do just a summary of the course. It's not that much that we have done. I mean, depend how much we want to go in details. But basically, what have we done? So this is, if you want, all the knowledge that you need to know is here and then the moments. Equations plus figures. No? Then combine loading, find the loads, find the combined stresses, normal and shear. Next thing we have done is what? Static fellow criteria, we have done what? The principal stresses. The max. Shear stresses and the volumetric stresses. And finally, what have we done? The dynamic failure criteria. If you want, I want to put 3. If you want, we have done the Goodman line. Modify Goodman lines and then the von Mises criteria. Okay, so I think did you have an assignment for today? You have something for next week, no? For Tuesday?
Yeah.
Okay, so my plan is that unless, I mean, you want to cover something specific, are you interested in something? Do you want me to cover in this class? Are you interested? Do you want me to cover the stuff on how to find the stresses, for example, on the reinforced concrete? That'd be cool. So next time we do that, and then probably I'm going to do the following class. I will do a class. If you have questions, the solution of the assignment. And what I'm going to be doing then is I will just come to class, every single class with a plan that we all work on it. Is that okay? And then we're going to be doing all the way to the semester. So if there is something you want to work on, let me know, and we can do for us about that stuff more specific. Okay? Hold on a second. Yes.
What
Day is what? Remind me next time we check it. Okay? I mean, let's say now. Yeah, that's great. That's why we're gonna find out now the exam date. So. And